Hi, this lesson is on the limit laws and the squeeze theorem. We start with limit laws. Suppose c is a constant and that the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist. The first limit law says that the limit of the sum of two functions is equivalent to the sum of the limits. The second one is related to the first one. It says that the limit of the difference of two functions is equal to the difference of the limits. Number 3 is used really often, says that the limit of a constant times a function is equal to that constant times the limit of the function. So you could actually factor out that c out, evaluate this limit, and then multiply by that constant. The fourth one has a special name. It's called the product law for limits. And it says that the limit of a product of two functions is equivalent to the product of the limits. And number 5 also has its own name called the quotient law for limits. It says that the limit of the quotient of two functions is equal to the quotient of the limits, but here there is a restriction. The one in the denominator cannot equal 0. Remember, division by 0 is undefined, so we know that the limit of g of x must exist. That's a condition of these limits, and 0 means a limit exists, but in the case of quotient law, that 0 cannot be in the denominator. And number 6 is the most convenient one to apply. It saves a lot of work. It says, and it's in two parts, the limit as x approaches a of f of x to the nth is equal to the limit as x approaches a of f of x raised to the nth power. The way it's written on the left side, you'd have to raise a function to the nth power. And we know that that could be a pretty busy process. So like imagine having something like this raised to like the 10th power. That would take a very long time. And that's something we probably would not want to do. So the right side says, well, you could take the limit of f of x, the inside part, and then whatever that number is, raise it to the 10th power. So the left side is a lot of algebra. The right side is pretty much just a numerical computation for the most part. And the second part is really similar. This says that you would have to take the nth root of f of x and then evaluate the limit. But on the right side, I would evaluate f of x. That would give me a number because the limit exists, and then take the nth root of that number. And n must be a positive integer. So we're going to apply some of these limit laws. Given that the limit as x approaches 3 of f of x is equal to 4, the limit as x approaches 3 of g of x is equal to negative 2, and the limit as x approaches 3 of h of x is equal to 0, we will use the limit laws to evaluate the following. So part A says that we have the limit as x approaches 3 of 5 times f of x over g of x. So I'm going to be using limit law 3 because I have a coefficient in front of the f of x, and quotient law because I am dividing g of x by 5 times f of x. So applying the laws looks like this. That is equivalent to 5 times the limit of f of x divided by the limit of g of x. Now we know what these values are. F of x's limit is 4. G of x's limit is negative 2. So I just plug in those numbers. 5 times 4 is 20 divided by negative 2. So my limit value is equal to negative 10. In part B, I'm going to be using the product law, and which is number 4, and law number 6, because I am multiplying two functions, but the second one I am taking the square root. So when I apply the laws, it should look like this. It's the limit as x approaches 3 of h of x times the square root of the limit as x approaches 3 of f of x. Now, h of x, that limit is given to be 0. The limit of f of x is 4, so I have 0 times the square root of 4. We know that square root of 4 is 2, and 0 times 2 gives me an answer of 0. Okay, now we go to part C here on the right. I have the limit as x approaches 3 of g of x to the 4th power over h of x. Here again, I'm using the quotient law because I am dividing these two functions, and I'm using this law number 6 because I have this function g of x raised to the fourth power. So when I apply the limit laws, it should look like the next line. So the limit as x approaches 3 of g of x raised to the fourth power divided by the limit of h of x. Now I plug in what I know. G of x is -2, h of x is 0, and this is exactly that scenario where your denominator cannot equal 0. Here it does, so this limit does not exist. Or at least we can't apply the limit laws here. Now there are other ways to evaluate limits. And we're going to learn a lot of them. And so one method is to use direct substitution, and you can always apply direct substitution to evaluate a limit as long as the value that x is approaching is in the domain of the function. X squared plus 3x is a quadratic function. It's a polynomial function, so the domain is all real numbers. So you can certainly evaluate this limit by just plugging directly into your function, and I get 2 squared plus 3 times 2 gives me a value of 10. If I apply the limit laws like I did here on the right, I get the same result. I'm just going to break it down into more steps. So here I applied the first law, which is regarding the sum. So the limit of a sum is equal to the sum of the limits. And I also applied the one regarding coefficients by putting the 3 here, or factoring out, putting it in front of the limit. Then, again, by direct substitution, plug in the 2, you'll get 2 squared and 3 times 2, which gives me the same result. My limit value for this function is 10. Okay, what happens when you can't apply direct substitution? In previous sections, we did this by numerically by plugging in numbers really close to the number that you're trying to evaluate. But we're moving away from that method. It's very tedious and time consuming, and there's definitely easier ways. But in this case, I can't just plug in the 2, because if I did, I would get 0 in the denominator. So we can do a little bit of algebraic manipulation to get us to a point where we can use direct substitution. And the method that we're going to use is to factor. So both the numerator and the denominator of this expression can be factored. The numerator factors into x plus 4, x minus 2, and the denominator factors into x times x minus 2. Once I have factored these, the x minus 2's cancel, and I'm just left with this limit. And now at this point, I can apply direct substitution where the x's are. So I get 2 plus 4 over 2, which is 6 over 2, which equals 3. So this is another example of where this function, let's say this is f of x, f of 2 does not exist, but the limit does, right? The limit is equal to 3. So in terms of what this would look like on a graph, there would be a hole. There would be a hole in this graph of this function at the point 2, 3, right? That's the value that x is approaching, and this is the value that the y value is approaching. But it would be open, an open circle, not a closed circle. Okay, so here's another one where we need to factor in order to solve this or evaluate this limit. You can't just plug in the 2 where the v is, because I would get 0 in the denominator. This time only the numerator factors, and it factors into 4v times v minus 2, but then the v minus 2's cancel, and I'm just left with the limit of 4v. Now you can plug in what v is approaching, which is 2, and again I get a limit value of 8. This one would also be one where there is a hole at the point 2, 8. 2 because that's what v is approaching, 8 because that is the value of the function, or what the function is getting close to as v gets close to 2. Okay, notice in both example 3 and 4 that you write the limit in front of the expression the whole time that you are simplifying. You stop writing the limit when you do the direct substitution. So I have a limit here, I have a limit here, I have a limit here. But when I plugged in 2 for the variable, then you no longer write the limit. Having good clean notation is really important, and it will become more and more important as you take higher levels of mathematics, because it's part of the language of how you communicate the mathematics is to have a clear, good notation. All right, here's another one where I can't just plug in the value of x. I can't plug in 3. That would give me a 0 here, but I can factor. So when I factor the numerator, it factors into x minus 3 and x plus 1. So this x minus 3 looks a lot like the denominator, but not quite. It's off by a sign. So what I did was I factored a negative 1 from the denominator, and I get negative parentheses x minus 3. And when I do that, then I can simplify, and I'm left with just the limit as x approaches 3 of negative parentheses x plus 1. And when you plug in 3 in here, you get negative 4 as your result. So again, you write your limit in front of the expression all throughout while you are simplifying, and then at the very end, when you plug in the negative 3, I didn't really write that step, but that's what it would look like, and that's where we get negative 4. Okay. Here's another one where we do need to factor, but it is a little bit different. They're not polynomials. I have exponential expressions in the numerator and the denominator. I have the limit as t approaches 0 of 5 to the 2t minus 1 divided by 5 to the t minus 1. Again, I can't just plug in 0 in here. If I did, I would have 5 to the 0 minus 1. 5 to the 0 is 1. And that would give me a 0 in the denominator. A 0 in the denominator does not mean that the limit doesn't exist. Like we see here, if I plug in 3, this would be 0, but the limit did exist. So you can't make that assumption, and be really careful not to do that when you are doing homework and assignments. So a 0 in the denominator means the function doesn't exist. It doesn't mean that the limit doesn't exist. So I'm going to use a similar technique to what I did in all the previous examples, and that is factoring. Here, the numerator is factorable if I treat it as the difference of perfect squares. So 5 to the 2t minus 1 is equal to 5 to the t plus 1 times 5 to the t minus 1. Remember, if I were to multiply this out by the FOIL method, when you do 5 to the t times 5 to the t, the rule says to add the exponents. So t plus t is 5 to the 2t. So that's where that first term comes from. And then the positive 1 and the negative 1 means that your outer and inner term will cancel, and you'll get minus 1 as your second value. So by factoring that, then the denominator will cancel with one of the factors in the numerator. So all I need to do is evaluate this limit of 5 to the t plus 1, and plugging in 0 in here will give me 1 plus 1, which is equal to 2. Oops, I didn't mean to move that. Okay. So try to put that back to where it was. I think it was here. Yeah. All right. So now I have example 7. So in example 7, I did it 2 different ways, and you have that option. I want to evaluate the limit as x approaches 0 of x plus 7 to the second power minus 49 over x. So first, let's look at how I did it on the left side. So on the left side, what I did was I expanded the x plus 7 squared, and that gave me x squared plus 14x plus 49. Then the 49s cancel each other out, and I'm left with this limit, x squared plus 14x over x. Factor out an x from the numerator, then the x in the numerator cancels with the x in the denominator, so I'm just left with this limit to evaluate, and when I plug in 0 for x, you get a limit value of 14. Now the way it's done on the right gives you the same result, and so either option is fine. What I did was I treated this as the difference of perfect squares, where the x plus 7 squared is like your a squared, and the 49 is your b squared. The formula says that it's a plus b times a minus b. So my a is the x plus 7, and the b is 7, because the square root of 49 is 7. And then this is the a and the minus b according to the formula, all over x. The first parenthesis simplifies to x plus 14. The second parenthesis simplifies to just x. And now this line right here looks just like this line. And so we end up with the same result. The x's cancel, and I'm left with the limit as x approaches 0 of x plus 14. And when you plug in 0 for x, you get the same value, that your limit value is equal to 14. Okay, so now we're going to talk about a new function which may be brand new for you, and it's called the greatest integer function. And it's a nice function to help explain limits and the behavior of graphs. So what is the greatest integer function? It looks like this, with these kind of double brackets around the x. Sometimes it's also written like this without the double lines. And what it represents is the largest integer that is less than or equal to any real numbers. So you're going to be rounding downward. Ignore all of your usual rounding rules. Any number that's inside the bracket, unless it's an integer, will always be rounded to the left. You'll always go less than that number. If it is an integer, it's just equal to itself. So, for example, the greatest integer for 2.3 is 2. The greatest integer for 4.9 is 4. Again, you're ignoring usual rounding rules. So you wouldn't say 5 the way we normally would when you round. You're always going to go to the left, or smaller numbers. The greatest integer for negative 1.07 is negative 2. Remember, negative 2 is to the left of negative 1.07, and so you're going to the left or downward, or less than. Negative 24.5, the greatest integer there is negative 25. The greatest integer function for pi, remember pi is about 3.14, so the greatest integer for pi is 3. If you have an integer inside of the greatest integer function, it's just equal to itself. So the greatest integer for 5 is 5. The greatest integer for 0 is 0. And you can also apply this to fractions. The greatest integer function for 2/3 is equal to 0. 2/3 is a number between 0 and 1. So remember, so it's going to be less than or equal to the number that is inside of the bracket. It's only going to be equal when the number itself is an integer. Okay, so the graph of the greatest integer function looks like what you see here on the right. It looks like a bunch of steps with a solid point to the left of each step and an open circle to the right of each step. And you are stepping according to what the integer is. So, for example, the greatest integer function for 0 is 0. That's why I have a solid point here. And 2/3 is between 0 and 1, so that's also equal to 0. So that's why I have a horizontal line representing all values between 0 and 1. But once I get to 1, the greatest integer function for 1 is 1, so that's why it jumps up. And anything between 1 and 2 will round down to 1. So that's why I have a horizontal line between 0 and 2 right here. But at 2, it steps up or jumps up to 2. And so that will be true all throughout for every single integer. So what does that mean in terms of limits? So here it says to evaluate the limit as x approaches 5 of the greatest integer function. Well, remember, for a limit to exist, the limit must be the same to the left of the number and to the right of the number. And because of the nature of greatest integer functions, that will not be true whenever you are approaching an integer, and 5 is an integer. Fractions are not integers, decimals are not integers, but 5 is an integer. So as I get closer and closer to 5 on the left, let's say a number like 4.9, like this one, the answer is 4. But when I get closer and closer to 5 on the right, a number like 5.1 would round down to 5. And so my left-hand limit and my right-hand limit are not equal, and therefore you can conclude that the limit as x approaches 5 of the greatest integer function does not exist. Now, if you happen to evaluate a limit at a number that's not an integer, then it will exist. Because whether I am close to 0.45 to the left of it or to the right of it, like let's say 0.445 would be to the left, that would equal 0. And if I was a little bit bigger than 0.45, let's say like 0.451, that would also round down to 0. So in that case, the limit would exist. So the greatest integers function, the limit does not exist when the value of the variable is approaching an integer. Not true if it's approaching something between the integers. All right, so here's another one with the greatest integer function. Evaluate the limit as t approaches 0 of 2 times the greatest integer function of t. So 0 is an integer, so I expect this to not exist, but we have to prove it, and the work that I show here is proving it. The limit from the left, so think of a number to the left of 0 would be something like negative 0.1. That rounds down to negative 1. So 2 times negative 1 means that my left-hand limit is equal to negative 2. But when I am on the right of 0, a number like 0.1 would round down to 0, and 2 times 0 is 0. Left-hand limit and right-hand limit are not the same, and so therefore the limit does not exist. So if you're asked to show if a limit exists or not, that's what you're looking to prove, if the left-hand limit and the right-hand limit are equal. In this case, the limit doesn't exist, and that's how we showed that. Okay, so here are other examples, not greatest integer, where we are using other algebraic techniques to evaluate a limit. So we have the limit as h approaches 9 of h minus 9 over the square root of h minus 3. I did this in 2 different ways. With method 1, I use the concept of conjugates. So the conjugate of my denominator, which is root h minus 3, is root h plus 3. Multiply that in the numerator and the denominator of the original expression. Remember, this is equal to 1. So when you multiply an expression by 1, you're not changing the value of the original function. You are maintaining its integrity. It's just a trick to help us come up with an answer. So if I multiply this out, I'll get h minus 9. So your foiling, your outer and inner terms will cancel. But in the numerator, don't expand it, because if you do, you're not going to realize what will cancel. Because I do want this h minus 9 to cancel with this h minus 9. So the limit that I have to evaluate is root h plus 3. Then you can plug in the 9 where the h is, and you end up with 6 as your limit value. So that's one method. You don't need to do it multiple ways. Just one method is fine. So whatever one you like best works fine. So what I did is I factored the numerator and I treated it as the difference of perfect squares, even though it's not a traditional perfect square. We're used to seeing things like this when we talk about a perfect square. I'm going to force it to be because I know that root h times root h equals h. So I factored this into root h plus 3 times root h minus 3. This root h minus 3 will cancel with the 1 in the denominator, and then I'm left with this, which is the same place we were here. And then you can plug in the 9, and you get the same result, that your limit value is equal to 6. So the second method is a little bit faster, but you get the same result either way. Okay, so here we have a limit with trigonometry. Remember, you can only apply direct substitution if the value that your variable is approaching is in the domain. Sine and cosine have a domain of all real numbers, but tangent is undefined at pi over 2 in every pi units to the left and right of pi over 2. So pi over 4 definitely works. So I can actually evaluate this by direct substitution. I don't have to do any kind of tricks or factoring um, or manipulate my trigonometry at all. So I did take a little shortcut here before I applied direct substitution because I noticed that one of the um, Pythagorean identities exists. So I factored out a 2. Remember, sine squared of theta plus cosine squared of theta equals 1. So that saved me a little bit of work. And then all I have to do is plug in the pi over 4 here for tangent. Pi over 4 is a 45-degree angle. Tangent is equal to 1 at that angle. So your answer is 2. So you are expected to know some basic trig, like common angles like pi over 4, pi over 3, pi over 6, and all the quadrantal angles and all of those 30, 60, 90, and 45-degree angles in all 4 quadrants. All right, here's another one that also has another radical, which does require us to do some manipulation. And again, I'm using the concept of conjugates. So I'm going to multiply the expression by the conjugate of the numerator, the one that has the radical, and that's going to be square root of t squared plus 9 plus 3 and square root of t squared plus 9 plus 3. And that's just equal to 1. And multiplying by 1 doesn't change the identity of the original problem. So when I FOIL this out, this square root times this square root just gives me t squared plus 9. My outer and inner terms will cancel, and then my last is minus 9. So in the numerator, I am able to cancel the 9's, and in the denominator, just put them next to each other. Don't distribute the t squared. That's not going to help. You want to see what you can do in order to cancel. And at this point, you can cancel because the t squared in the numerator will cancel with the t squared in the denominator, and I'm just left with 1 over the square root of t squared plus 9 plus 3. Now we can apply direct substitution. Remember, when you apply direct substitution, you no longer write your limit. Just plug in the number where the variable is, and I end up with 1 over root 9 plus 3, which gives me an answer of 1/6. So it's another example of that where the limit exists, although the function does not at t equal to 0. Okay, here's another one where we are going to use some algebra principles to evaluate this. So I have what we call a complex fraction. I have fractional expression inside of another fraction. So um, I'm going to use LCDs to make this look better. So the common denominator for these two fractions is a times h. So the first one gets multiplied by a over a. The second one gets multiplied by h over h. So on the next line, that's exactly what you see. I have a minus h over the common denominator of ah. Doesn't matter if you write it as ah or ha. It's the same thing. And I left the denominator alone. So now I can see that this and this kind of looks similar. This happened in a previous example, except they're off by like a sign. So I first rewrote this division symbol as a times symbol and took the reciprocal of the denominator. So I have a minus h over ah times 1 over h times a. And then here I factored out a negative 1 from the denominator. So therefore this a minus h and this a minus h cancel each other out, and I'm left with negative 1 over a times h. As h approaches a, that means you plug in a right in here, and you end up with an answer of negative 1 over a squared. So this one's a little bit more abstract because you don't have any numbers, but the concept is very similar to previous examples. Okay, if you don't remember how to get common denominators, you can look up LCD for rational expressions. That would be something you could look up like on YouTube or a Khan Academy, and they would explain that. Or you can look up simplifying complex fractions, which is exactly what we had here. And then you would need an LCD in order to do that. So if there's ever anything using algebra or pre-calculus that you don't remember, you really should try to figure that out before you continue in a calc class, because that just gets messier as you move through if you don't know those concepts. All right, so the last part of this lesson is on a theorem called squeeze theorem. It's also called the sandwich theorem or the pinch theorem. So I guess the idea is that you're going to have one function that I'm calling g of x in the middle of two other functions. So if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, except possibly at a, and if the limit as x approaches a of f of x equals the limit as x approaches a of g of x, and they both equal some value L, so in other words, these two limits must be the same and they have to exist, then the limit of the one in the middle must have the same limit. So why do we need this theorem? Sometimes it is very difficult to evaluate the limit of the function in the middle, but it's quite easy to evaluate the limit of the one that is below that function and the one that is above that function. So we can avoid evaluating this limit as long as we can get some information about the other two. So you have to first have this scenario where you have one function in the middle of two other functions. So graphically, f of x would be below g of x. Let's say this is some value here, a. This is g of x. And then h of x would have to be above it at a. So that's more or less what it would look like. So what the theorem is saying is if you can establish a relationship like that, like an inequality like this, and you can show that the limit of the function that's below and the limit of the function that's above both exist and are equal, then you can draw a conclusion that the limit of the function in the middle has the same exact limit value. So here's our first example. If 4x minus 9 is less than or equal to f of x, which is less than or equal to x squared minus 4x plus 7 for values of x greater than or equal to 0, find the limit as x approaches 4 of f of x. So we are told that this inequality exists. So we already have this part of your theorem. So The first part is given, so that's good news. I don't know what f of x is. I just know it's somewhere in the middle of those two other functions. So now I have to show this part. I have to evaluate the limit as x approaches 4 of 4x minus 9 and the limit as x approaches 4 of x squared minus 4x plus 7. Why 4? Because that's what we're trying to figure out for the one in the middle. So the first function, 4x minus 9, is a line. I can just evaluate this by direct substitution, and I get 7. The second function, or the one that's above, is a parabola. Again, all real numbers are in the domain, so by direct substitution, you plug in 4 squared minus 4 times 4 plus 7, and you also get 7. So the limit of the function that's above and the limit of the function that's below and above are both equal. So we've proven this part. And because we have the first part and the second part, then you can conclude that the one in the middle that we're calling f of x in this problem is also equal to 7. Now we don't know what f of x is, but here's the graph. The 4x minus 9 is the line in red. The parabola is in dark blue. Here's the value at 4, and so that is 7 right here. So if I had any graph f of x going through this, notice it's squeezed so tightly for that to be in the middle of these two. The only way that g of x could have the same exact limit, the only possibility has to always be the same value that we got here and here, because it is being squeezed between these two. And they really are very close to each other. It's hard to distinguish the parabola from the line when you are close to x equal to 4. So if you have like a graphing calculator and it allows you to zoom in on 4, you'll be able to see that the line is below the parabola when you are close to 4. Okay, here's another one. Says use the squeeze theorem to evaluate the limit as x approaches 0 of x squared over cosine of 5 over x. So this time I didn't give you a nice inequality the way I did in this example. So we're going to have to come up with one based on what we know about trigonometry. Now the cosine function, graph of cosine looks like this. It oscillates up and down between positive 1 and negative 1. The y values are never bigger than positive 1 and never smaller than negative 1. So it is safe to say that this inequality is true just for cosine. That negative 1 is less than or equal to cosine of 5 over x, which is less than or equal to 1. But that's not what I'm trying to evaluate. I have this x squared there. So I'm going to take this inequality and multiply all three sides by x squared. So that means the negative 1 gets multiplied by x squared, the cosine gets multiplied by x squared, and the 1. So my new inequality is negative x squared less than or equal to x squared cosine of 5 over x less than or equal to x squared. And now this is the first condition in squeeze theorem. I have an inequality established where the limit of where the function that I'm interested in is in between two other ones. Now I have to do the second part. The second part is the limit of the function that's below and the limit of the function that's above the same? And we see that it is. The limit as x approaches 0 of negative x squared, well, by direct substitution, that gives me 0. The limit as x approaches 0 of x squared, that also gives me 0. Since the limit of the function that's below and the limit of the function that's above are the same, then you can draw your conclusion that the limit of the function in the middle is also equal to 0. Okay, here's another one. This time we're using the sine function. Use the squeeze theorem to evaluate the limit as theta approaches 0 of theta to the fourth sine over theta squared. again, using what we know from trigonometry, your sine function oscillates between -1 and 1. So your sine function looks like this in just one period of it. So this, and then it comes back down. So this value, the highest value here is 1. The lowest value down here is -1. And so there, I can safely say that this is true from what we know from trigonometry. But I'm interested in this function. So I need to multiply this, all three sides, by theta to the fourth power so that the middle looks the same as what I'm interested in. So when I do that, you'll get the next line, and that is that negative theta to the fourth is less than or equal to theta to the fourth sine of 1 over theta squared, which is less than or equal to theta to the fourth. So that was the first condition in the theorem. Now I have to do the second condition, which is here. Show that this limit and this limit as theta approaches 0 are both the same. So again, by direct substitution, the first one is 0. This should be to the fourth. This should be to the fourth. And the second one is also 0. Since they're both the same, then you can conclude that the one in the middle has the same limit. Okay, there's no such thing as a -0, so this negative here doesn't have any impact. Okay, here's another one where we use squeeze theorem. And again, it's referencing a previous lesson. So use squeeze theorem to evaluate the limit as x approaches 3 of x squared minus 9 over x minus 3 over the absolute value of x minus 3. So in a previous lesson, I showed you that when you have an absolute value in either the numerator and the denominator and the same expression without the absolute value in the numerator or denominator, then your limit as you get closer and closer to 3 is either going to be +1 or -1. So we can isolate this part based on previous experience and say that -1 is less than or equal to x minus 3 over the absolute value of x minus 3, which is less than or equal to 1. And then apply the same trick that I applied in previous examples, which is to multiply all three sides of this expression by the part that's missing, which is x squared minus 9. So this is the first thing you have to show with squeeze theorem, is that the function that you're interested in is being squeezed by two other functions. So I have negative parentheses x squared minus 9 is less than or equal to x squared minus 9 times x minus 3 over the absolute value of x minus 3, which is less than or equal to x squared minus 9. So now I have to work on this and evaluate the limit as x approaches 3 and see if those values are the same. If they are the same, then I can evaluate the limit in the middle. So the one below has a limit value of 0. The one above also has a limit value of 0. Since these two are equal, then you can conclude that the limit of the one that's in the middle, so this is what I mean by the middle, also has the same limit value. So this was the second part that needed to be proven according to squeeze theorem, and that's it. So good luck. Give the homework a try.